So now that we've done some work with parallelograms and seen ways of proving that things are parallelograms, we can go back and actually look at another parallel line theorem, this one called the weak 3 parallel line postulate. And this one doesn't have to do with two parallel lines and transversals. It has to do with a particular circumstance of when we have multiple lines that are parallel to each other, and then lines or segments or rays that are transversals of all of them. And we are going to use the properties of parallelograms to actually show what we want to as a part of this postulate. So what we call the weak 3 parallel line postulate is exactly this. If 3 parallel lines cut off congruent segments on one transversal, then they cut congruent segments on every transversal. Or in other words, if AD, BE, and CF are all parallel to each other, and we have a transversal ABC, so that AB and BC are congruent, it means then that DE and EF will also be congruent. And if we add another transversal at an even more extreme angle, or even at a less extreme angle, then the segments of that transversal that are cut by the parallel lines will also be congruent. One transversal cut into congruent segments is enough. So go ahead, pause the video, write down the statement of the weak 3 parallel line postulate, as well as the diagram, at least the diagram that we initially had, showing that all of the transversals are cut into congruent segments by the parallel lines. Come back when you are ready to see the proof. Okay, so now let's take a look at the proof. In this case, what we're given is that AD, BE, and CF are all parallel. We also know that AB is congruent to BC, because that is the if statement of the 3 parallel line postulate. What we want to prove then is that DE and EF are also congruent. And the way that we're going to do that is we are going to add segments DX and EY into the diagram so that, and this will be the first step that I put in my proof, your first step again is going to be the given, is that DX is parallel to AB, and that EY is parallel to BC. And the reason for that is construction, because we have added a series of segments onto our diagram. Okay, great. So now we have AB and BC that are congruent, we have DX that is parallel to AB, and we have EY that is parallel to BC. Well, now we have two new quadrilaterals that we've created, ABDX, or ABXD, and BCYE, that have two sets of parallel sides. We know that AD, BE, and CF are all parallel, and we know that AB and DX are parallel, and we know that BC and EY are parallel. So what does that mean? Our two quadrilaterals that we've just created are parallelograms by the definition of a parallelogram. So the next step in that proof is that ABXD and that BCYE are both parallelograms by the definition of a parallelogram. Again, I'm going to take some shortcuts for the sake of space on the screen by using that figure to represent a parallelogram, even though that is a very badly drawn parallelogram, admittedly. So that's what we know. By constructing those segments, we've created parallelograms. Well, one of the properties of parallelograms is that opposite sides are congruent. We saw that previously in this module, so we can use that now because we proved it. So we know that DX is congruent to AB, and I'm going to string all of these together by the transitive property, which is congruent to BC, which is congruent to EY, and that is because of the properties, is one of the properties of a parallelogram. And again, for the sake of space, I'm going to string these all together using the transitive property. So DX is congruent to AB, is congruent to BC, is congruent to EY. Great. Well, how does that help us? Well, it tells us that two other segments are congruent, and now we can start looking at triangles DXE and EYF to say, can we find congruent triangles so that DE and EF, which are the corresponding parts of those triangles, can be said to be congruent? Well, there are a few different things that we can do here. We know that DF is a transversal for parallel lines AD, BE, and CF. So therefore, we know that some of these lines, or some of these angles, are going to be congruent because they're corresponding angles. So that includes angle DEX being congruent to angle EFY. Why? Because of the corresponding angles theorem. And the next set of angles is not quite as straightforward, but it also involves corresponding angles. And it comes from the fact that we know that DX is parallel to AC, the whole line, because AC is a line that's a transversal, and EY is also parallel to AC. That comes back from the way that we did that construction. So because of that, DX parallel to AC, which is parallel to EY, we know that DX is parallel to EY. Why? Because parallel lines are transitive, at least on a plane. That is, a line that is parallel to one line and another line that is parallel to that first line, then all the lines are parallel. So that comes from transitive parallel lines. Great. Well, if DX and EY are parallel, then DF is now also a transversal for the segments DX and EY that are parallel, which means we have a new set of corresponding angles in the case of XDE and YEF. And that is again because of the corresponding angles theorem. Great, so now we have two angles and a non-included side of two triangles being congruent, which means that we can use angle side and say that triangle XDE is going to be congruent to triangle YEF. That is because of ASA. And then finally, because we have congruent triangles, we can say that DE is congruent to EF. All because of the most useful property of congruent triangles, and that is CP-CTC. So that is the proof of what we call the weak 3 parallel line postulate. That is, if we have 3 parallel lines that cut congruent segments on one transversal, they must cut congruent segments on every transversal.